Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 21, part B, and we are going to finish up talking about randomized complete block designs. This is the only topic we're going to cover in chapter 4 in this course because we want to talk about more topics, and the rest of chapter 4 includes Latin square designs and incomplete, unbalanced block designs. And so those are not as common designs as some of the others that I would like to expose you to before you go out into the real world or grad school. So last time we talked about fixed effects, that both the treatments and the blocks are fixed effects. That is not actually a very common occurrence. It's more common for us to have at least one random factor. So there's many situations where the treatments are random, the blocks are random, or both are random. But it is extremely common to find that the blocks are random. Okay? In fact, in the hardness tester example that we had, our blocks should be random because those were 2 heats or batches of raw material. And we don't want our results to only be good for those 2 batches of material. We'd like the results to extend to all possible heats or batches of materials, and the way we do that is by randomly selecting those 2 heats or batches for the experiment. And then we can extend our results to the entire population of batches for that, at least from that supplier, for that alloy. Okay? So we're going to talk about something called a mixed model. That is that we're mixing fixed effects and random effects in the same model. So, and again, it's very common. In fact, it's probably the most common model for complete random or randomized complete block designs is to have a random block effect and a fixed treatment effect. So that's the reason the textbook has chosen to use or highlight this model. Okay, so the model is y sub ij equals mu plus tau I plus beta j plus epsilon sub ij. Remember that k is equal to 1, so it doesn't show up as an indice. I goes from 1 to A, J goes from 1 to B. Since the treatment factor or effect is fixed, then the constraint is that the sum of the tau i's is equal to 0. And again, this is a very logical assumption because we have mu, so mu plus tau I is equal to mu sub I. And so tau sub I equals mu sub I minus mu. And so mu is a constant, and then the different mu i's, especially if it's a balanced model, then we expect all of these differences to add up to, so if we add up all the tau i's, then we would have mu 1 minus mu plus mu 2 minus mu plus minus mu plus mu a minus mu. And if we add up, if it's balanced, then mu 1 plus mu 2 plus mu a should be equal to a times mu. Okay? So that means that the sum of the tau i's should be 0. All right, so that's the logic behind it. I think I've explained it before, but I wanted to review that. Now that we've seen it a few times, hopefully it makes more sense for this explanation. Okay, so the random blocks. So beta sub j is random, so that means it has a normal, independently distributed distribution with mean 0 and variance sigma sub beta squared. And in all models, the errors are random, and they have a normally independent or identically distributed, they are independent, but they are normally and identically distributed with a mean of 0 and a variance of sigma squared. Okay? if we want the expectation of y sub I, remember that y sub ij is this. So we substitute in. We're not going to derive all these. I'm just going to show you the first one. E of yij is equal to E of mu plus tau I plus beta j plus epsilon sub I j. And of course, this expectation distributes across the linear operator, the summation. Okay, it's a linear operator. So the expected value of a constant mu is just going to be mu. The treatment effects, the tau sub i's, they're constant as well because they're fixed. So the expectation is going to be tau sub I. But the beta j's have a normal distribution with mean 0 and variance sigma sub beta squared. So this is E of beta j. That's 0, so that's going to be 0. And if you look up here for the epsilons, their mean is 0. Their expected value is 0, so plus 0. So this gives us mu plus tau I, and that's how we got this. I won't do the others because we did it in another model, or in the fixed effects version. So there's no need to repeat that. You can go back to the previous video and see how we did that if you're interested. But the variance of y sub ij, again, there's no variance for mu because it's a constant, and no variance for tau because it's a constant. So the only variances that we have are for the random effects. So we add those two together because they are independent. And then we look at the covariance for observations in different blocks, and they're going to, that covariance, because is going to be 0 because they're independent, okay, for j not equal to j prime. And I don't believe I'm supposed to have an I prime there, just a j prime. And then if we look at the same block of material, okay, but different treatments, then we see that before the experiment is performed, because they're from the same batch of material, we expect those hardness measurements to be correlated or dependent since they're from the same distribution, and that variance is sigma sub beta squared. Okay, and again, this is for I not equal to I prime. So for different treatments but the same batch of material, we expect the covariance between the observations to be the variance of the batch that they're in. Then we look at the expected mean square of the treatment, and we can write it in this form. Sometimes this value is substituted for this value, and we can think of this as a variation. And so sigma squared plus b times sigma sub a squared, where a is the treatment effect. And so sigma sub a squared is the sum of tau I squared over a minus 1. And when you think about this, remember that tau I is, let's see, so mu I equals tau I plus mu. So that's going to be mu I minus mu. And you can think of this as the mu sub I bar if you want, the overall average. You can think of it as but it is a mean, and so we're subtracting from the mean, and we're squaring, and then we're taking over a minus 1. This looks very much like a sample variance. Sample variance because of the a minus 1, but we have population parameters here. So it's not, but it's like a variance, okay, a sample variance. And then we have the expected value of the mean square for beta. And these are independent, so we end up with sigma squared plus sigma sub beta squared. And sigma sub beta, this is a point estimate that can be obtained with the method of moments. It's a method of moments estimator. And so from the ANOVA table, ms sub b or beta minus MSE over A. And we'll talk about this. I'll go ahead and mention that sigma sub beta squared is a methods of moments estimator, and there's no simple way to find its confidence interval. You'd have to use restricted maximum likelihood methods. Okay, and so we've looked at E of MS beta, and then we have E of MSE is simply sigma squared, the error of the epsilon sub ij's, the random errors. And if we take a look at MSTRT over MSE, that is going to have, these are independent chi-square random variables. We've shown that before. And so their ratio is going to be an F distribution. And the degrees of freedom in the numerator is going to be the degrees of freedom of the TRT, or A. And the degrees of freedom in the denominator are going to be the degrees of freedom of MSE. And so we could rewrite this for the randomized complete block design, A minus 1 for the treatment degrees of freedom, and A minus 1 times B minus 1 for the error degrees of freedom. And this test is exactly the same test as when the blocks are fixed, okay? But it's behaving differently behind the scenes. Okay, and here's one of the major benefits of using a mixed design here. What if you do have some interaction? Okay, we just said for the fixed effects model in the last video that if you have interaction with a fixed effects, fully fixed effects model with fixed blocks, your results are useless. Okay, you may or may not be able to do a transformation that gets rid of the interaction. Okay. In our chemical example that we gave, chemical formulations, there was nothing we could have done in that case, the way the interaction occurred. Okay. So for a mixed model with random blocks, if there is interaction, then the model becomes this: mu plus tau I plus beta j plus tau times beta sub ij and epsilon sub ij. I goes from 1 to A, j goes from 1 to B. Remember, k is just 1, so testing for interaction is not possible. There's no way to test for interaction. We'll see that in Chapter 5. We need a replicate. We need replications in order to do that. Usually 3 or more. 3 as a minimum, usually. Okay. And the interaction term is random because beta j is random. And so if you take a constant times a random variable, it's a random variable that's scaled by the constants. It's still a random variable, right? If you take two constants and multiply, then you just get another constant with no variation, you see. So the interaction terms become random. So what does this mean? Let's look at what happens is when we have an interaction between the treatment and the block, then you're going to have, and this is a square, sorry, you're going to have a variance component for the interaction in both the MSTRT and the MSE. If the MSTRT is fixed, then you don't have variance. You don't have a variance component in the treatment effects, but you would have it in the error effects. Okay. So this becomes sigma squared plus the expected mean square of the treatment effects becomes sigma squared plus sigma sub tau beta, the interaction, squared, plus b times sigma sub a squared. Again, sigma sub a squared is the sum of tau I squared plus a minus I. Okay? And then the expected mean square of the blocks is simply sigma squared plus a times sigma sub beta squared. If I take an F-test now of MSTRT over MSE, we look at the expected values and we see that in the numerator we have sigma plus tau times beta squared, and we have the same thing in the denominator. The only difference between the numerator and the denominator is b times sigma sub a squared. So if tau 1 equals tau 2 equals tau A, you can show that they all equal 0 with a little algebra. So that makes perfect sense, actually. So if that's the case, if they're all the same, then that's 0. They're all 0, and then the sum of tau I squared would be the sum of zeros. That's going to be 0. Okay? And so that would mean that this would be, this implies that that would be 0. Okay? So if that's 0, then we have an F of 1. The ratio is the same. If the treatment effects are significant, then you're going to have a positive number here. It's always positive because it's a square. And the numerator will be larger than the denominator, and you'll be larger than 1. Okay? And again, this F statistic has F sub A has a F distribution with A minus 1 degrees of freedom in the numerator and A minus 1 times B minus 1 degrees of freedom in the denominator. So again, F sub A test for only the treatment effects. F sub A test for the treatment effects only, because this factor sigma squared plus sigma sub tau beta squared is in both the numerator and the denominator, and the only difference is when this term here is greater than 0, and that's what I was just saying. Okay? So in the fixed effects blocks, this would not be in the MSTRT. It would only be in the MSE, because here the blocks would be fixed. And so the interaction would make F sub A useless when we have fixed blocks. And there would be no test for the treatment effects. We couldn't test for treatment effects if there's interaction in the fixed effects. This is a very important thing to know. You need to be able to tell whether there's interaction or not, so that if you have a fixed effects model, you know that you can't do anything without getting rid of the interaction. So you may need to do replicates of the experiment so you can use factorial model to analyze. Okay? Now the last thing we want to talk about is the checking the model for its adequacy for meeting assumptions. Okay? So meeting assumptions. And we know how to do this. We have an extra plot that's going to be added, but we know that we need to check for normality, and we can use a QQ plot of the residuals. We also should know that we have to check for equal variances. And so now we have the residual versus the fitted or predicted values. And again, we don't want to see any relationship between the size of the residual and the fitted value Yij hat. Okay? There should be no funnel shape. We don't want to see an increase or decrease in the variance, in variation or spread across the fitted values. We don't want there to be any obvious pattern to the residuals as we go across the fitted values. And we don't want any one fitted value to have an obviously different spread or scatter or variation than the others. Okay? Now, the second plot we'll look at is the residual versus treatment, right? And again, we're looking for basically the same things as we did under the residual versus fitted. And now we add a new plot, the residual versus blocks. So we'll have our residuals up here, and we'll have the blocks down here. And we want to make sure that the spread or the scatter or the variation is approximately the same across all blocks. Otherwise, we could say that interaction exists. So this is how we figure out if we have interaction. So let's talk a little bit about this interaction. How would we recognize it? And what they're saying is we'd see something like, we might see something like this. Oops. So something where we see low values of residuals with the early blocks, and then intermediate for intermediate residuals we'd have for the middle block, and then for the other block we would have, is that what it says, for negative residuals with high Y sub hat values. I'm sorry, it's not across blocks, it's across the fitted, I'm sorry. So we don't look at the blocks to find interaction. Where'd that go? We look at Y, I, J hat, okay? So for the low values of Y sub I, J hat, we'd have a negative residual. For intermediate values, we'd have positive, and then for high values of yi, j hat, we'd have negative values of residuals. Of course, you could have it in reverse too. This is just one example. You could have it like this, and then like this, and then like this, and again, there would be interaction between the blocks and the treatments. Okay. So if this occurs, you want to try a transformation to see if you can eliminate it. Okay, I shouldn't mark through that. I meant to circle it, not mark through it. So this is something you want to try. Okay, so that's it for the randomized complete block design. Next time we'll look at we'll want to look at the code and see how we analyze this using our code. So if you have questions, by all means, come to virtual office hours. If you need help outside of office hours, then by all means, email me. But if you're asking about a problem, make sure that you send me a copy of the problem, because I may not have it available. And send me a copy of your work so far so I can see how you're approaching it, and that will help me help you. Please take care of yourself and stay safe, because we want to see you here next time.